Alright, welcome guys. It's my first video in quite a while, so I hope whoever watches this video is doing well. Today we're going to be going over some pretty simple electrochemistry topics. So starting off, just a review of oxidation and reduction. In oxidation, we know that electrons are in fact lost, and that's represented by our little mnemonic here, LEO, loss, electrons, and oxidation. On the other hand, we have that reduction is when electrons are gained. So Leo says GER, which is gain electrons in reduction. So in an oxidation reduction reaction, electrons are exchanged by reactants and oxidation states of some of the reactants, and are changed over the course of the reaction altogether. So just to kind of put that into more of a perspective of something you'll understand, it's just a transfer of electrons from one species to another species, and the transfer means that the number of electrons a certain substance or species is willing to give up is the exact number another species is willing to pick up. And this is something that we're going to explore soon. So for example, let's go through this equation. This is a redox reaction, and obviously right now you may not recognize that, but we can go through and we can fill out some of these oxidation states, which was one of the topics for the previous video. So in metallic pure form, the oxidation state for just iron is 0. The oxidation state for H plus in HCl is just +1. The oxidation state for Cl minus is just -1. The oxidation state for iron in iron 2 chloride is 2. And we know that for chlorine minus, it's just -1. Now for elemental or gaseous hydrogen gas or whatever, the oxidation state is actually 0. So for most of those diatomic gases, or actually all of them, when you're having it as, a molecule, it's going to have an oxidation state of 0. So just over here, I've uploaded some of the answers for this, so you can go ahead and check those. And yeah, so I want you to see that. Let's go back up to here so that we're on page. I want you to see that some of the species notice changes. They incur changes in the in the state of their oxidation. So for example, we see that this iron is going from 0 to 2 plus. So it's being oxidized by 2. Since it's being oxidized by 2, we know that there must be something that's being reduced. And in this case, let's notice that H plus is going from a +1 charge to a 0 charge. So it's gaining electrons that are making it less positive. So the hydrogen is being reduced while the iron is being oxidized. So down here, we can fill out that iron is being oxidized from +2 to 0, while hydrogen is being reduced. Oh wait, sorry. That was pretty dumb of me. It's actually, this is completely my bad, 0 to +2. We have that hydrogen is being reduced from +1 to 0. Now you might remember I said that you need to have the same number of electrons for both of them, right? So for example, you would want to have that iron is going to give up 2 electrons. Hydrogen needs to be able to accept 2 electrons. So we'll get into these half reaction stuff next, but essentially that's why if we go up to the original equation, we have two hydrogens that are present. So since there's a 2H plus, there are 2 charges that are ready to be accepted. So let's just move on to half reactions because that's the logical step after this. So half reactions break up the oxidation reduction reaction into 2 parts, the oxidation part of it and the reduction part of it. The change in the charge will represent the movement of electrons. So with the half equations, expect to see electrons. So staying with the same iron example, let's go back up. We know that iron is oxidized from 0 to +2, while hydrogen is reduced from +1 to 0. So for the iron, we're going from iron solid to iron 2 plus. And since it has lost 2 electrons, we have these 2 electrons hanging out over here. And that represents that they're separate now, right? Iron and the electrons are separate as products. On the other hand, we see hydrogen was reduced. So with that in mind, you should see something slightly different. We know that it goes to H2, and it starts off as H+, but we're going to add electrons on this side. They combine to make H2. But here's the catch. In half reactions, or in essentially any type of reactions, oh, I forgot you can't see this. There we go. In any type of reactions, one thing is always important, and that is that you have to balance. You have to balance. So for example, you have 2 hydrogens on this side, but you only currently have 1 over here. You know what that means? We're going to have to stick a 2 over here. Now, are we balanced? The correct answer is no. Although we have balanced and elementally, there's an imbalance in charges. For example, let's look at the iron one that we just did. We know that the charge over here is 0. That's the wrong color. We know that the charge over here is 0. We know that the charge over here is 2 plus, and we have 2 electrons. So the 2 plus and the 2 electrons cancel out to make 0. So we have 0 on both sides. But here we have 2 plus. That's also the wrong color. Here we have 2 plus. Uh-oh. Here we have 2 plus, and we have only 1 minus, and we have 0 over here. So we're not forming 0. We still need to go down 1, and that's where, like I had mentioned a couple of minutes ago, you need to add on another electron. And there we go. We have made our oxidation reaction, so our oxidation half reaction and our reduction half reaction. This is the oxidation, and this is the reduction. Alright, there is the answers. So yep, remember, half reactions must also be balanced. Both the total charge and amounts of each substance must be equal. So for example, the hydrogen half reaction had 1 H plus on one side and H2 on the other side. So to balance it, 2 H plus must be created, but because of this, 2 plus charge is on the left side, while 0 charge is on the right. So instead of only adding 1 electron, we're adding 2 electrons to make this equation balanced. Okay, now that we have a general understanding of reactions, redox reactions, half reactions, and overall the oxidation world, we're going to move on to something that's a little bit more involved, you could say. And this is reduction potentials. This is going to be one of my favorite topics in all of chemistry, simply because there's so much you can learn in this. So it's also like applicable in other fields as well. Reduction potentials, if you've learned about membrane potentials in biology or just simply circuits and physics, it's literally everywhere. And this is like the starting of that. So essentially what it says is a movement of electrons creates a current, which also induces a voltage. So this electric potential or voltage that's created is known as the reduction potential, and it's unique to every species that is being reduced. Once again, reduction means there is a gain of electrons. So another way to think of reduction potential is like willingness to be reduced. Similarly how we had initially thought of, nonpolar versus polar, right? Something is more willing, nonpolar versus polar covalent. Something is more attracted to the electrons than other things. Similarly, some things are more willing to reduce than other species. So some substances might tend to reduce strongly, and they are associated with larger reduction values. So potential, voltage, it's all measured in volts, and it's a numerical scale. So for example, let's talk about reducing Zn2+, zinc 2 ion. So here we have the half reaction of, or I guess we could just say the reduction reaction of Zn2+. We have the gaining of electrons, which leads to the overall oxidation state to go from 2+ to 0. Here I can mark 0 over here. Uh-oh. Well, it seems like I forgot to not stop recording. So anyone who's watching this video is just going to see that really awkward phase in which I'm just drinking water and coughing. But okay. Where was I? Yeah. So we had just added on this 0 over here just to, amplify the idea that the Zn is being reduced. So on the other hand, there's another thing that's in this entire scheme, and we've been talking about reductions, where there's also oxidations. So potentials are always given as reduction half reactions, but if you want to know the chance of something being oxidized instead of it being reduced, just flip the equation and the sign of E, which is the reduction potential value, to get the oxidation potential. So for example, this reduction potential this reduction equation is associated with a reduction potential, which is in this case negative 0.76 volts. So if you flip the equation, we're finding how it might, how willing it is to be oxidized. So now, what do I mean by how willing it is? Since we reduce Zn2+, we're going to be oxidizing just Zn0, which is just solid zinc. So we flip the equation over here, and we also flip the sign from reduction potential to oxidation potential. So here you see there's a positive sign. So as mentioned before, the larger the reduction potential of a species, the more likely it is to get reduced. So let's take the previous example of zinc and consider it against fluorine. So we already know this. Now let's look at fluorine gas. Fluorine, this is the reduction equation for fluorine. So fluorine plus 2 electrons equals 2F minus. And it's represented by this value of reduction potential. So comparing this value to this value over here, what do you see? Well, you see that fluorine gas has a relatively large reduction potential when compared to Zn2+, which means that reduction potential is greater for fluorine than it is for zinc. And so, in a reaction where zinc and fluorine gas are transferring electrons, fluorine gas is going to be the one that reduces. And since it is going to be reducing, that means that Zn, or zinc metal, zinc solid, will be forced to oxidize. So, given this, we can actually calculate the overall reduction potential of a redox reaction. Right? So far we've been talking about reduction equations and oxidation half equations. But you can calculate the potential of just a redox reaction from the reduction potentials of its half reactions. So there are two steps. You add the potential for the oxidation half reaction to the potential of the reduction reaction, and number two, you remember that you cannot multiply potentials by coefficients like you might do for enthalpy, right? So, for example, like in Hess's law, you would have to, if you multiply an equation, like through with a coefficient, you'll have to like multiply the change of enthalpy as well with that same coefficient. That does not apply here. In no way does the actual value, or I should say the magnitude of the value of reduction potential ever change. Obviously, the sign will change depending on whether you're oxidizing or reducing. But other than that, you can't change anything. So just to get into you guys' head, we're going to go through this question. Question for comprehension. Below are relevant half reduction potentials. There, I made myself smaller so you can see the stuff. So, we have silver and we have zinc. Both of them are being reduced. Well, we don't know both of them are being reduced. We're just given the reduction potential of both of them. So you have to identify which species gets oxidized and which one gets reduced. Also calculate the reduction potential for the full redox reaction. Write the full redox reaction with its potential. If you want to find out the answer to this question, visit my website under Chemistry Lab and Electrochemistry. This document can be found and the answer is attached to it. Thank you guys for listening, and I'll see you in the next video.